Alright, I just wanted to create a quick video showing how we solve the differential equation for the tank drain. So we had this equation right here, this differential equation. So it was dH dt equals negative AJ over AT times the square root of 2GH. Alright, this is a differential equation because H, the height of the water, is a function of time. Okay, so you're going to find an equation of H in terms of T and all of the other constants. Okay, now this equation right here, it's a first order, it's a separable equation, so that means we can basically bring over H from the right side to the left and dt over there. Okay, so when we do this, it's dH over the square root of H equals negative AJ over AT times the square root of 2G, okay, times dt. So it's separable, first order, and we can just now integrate both sides. From T naught to T naught is 0, H naught to H. Okay. So now let's integrate. So we're going to integrate dH over the square root of H. So this is going to become H to the 1/2 because you add. Actually, let me make this a little easier for you. I'm going to write it over here. This could be square root of H on the bottom is H to the negative 1/2 times dH. Okay, so we're going to integrate that. Okay, so that's this term right here. So when we integrate that, we add 1 to the exponent, so it's H to the 1/2, and we divide by that. Okay, we're going to evaluate from H naught to H, and then over here, pretty much everything is a constant, times square root of 2g, so that can be brought out of the integral. And then we're pretty much going to integrate dt, which is times t from t naught of 0 to t. Okay, I didn't put h naught in as a number yet because that could change, but our initial time is pretty much always going to be 0. Okay, all right, now I'm going to write this again. This could be 2h to the 1/2 from H naught to H, and this is going to be negative AJ over AT square root of 2G times T from T naught of 0 to T. Now how do we plug these in? Well, you take the top, so this one, you're going to plug it in here. Okay, let me rewrite that so it's neater. H to the 1/2, and then you're going to subtract the bottom one and plug it in there. So 2h naught to the 1/2. Okay, same thing on the right hand side, negative AJ over AT times 2g times t, because we brought this in there, and then when we do this, minus a negative AJ over AT 2g times t, which is actually, we plug in t naught, right? But that's 0, so this whole term is 0. So we end up getting 2h to the 1/2 equals negative AJ over AT times radical 2g times t. Then I'm going to add the 2h naught to the 1/2 from the other side. I'm going to divide each term by 2. That takes care of that. And then what we need to do is we take this entire thing and we square it, okay, to get rid of the 1/2 on the left-hand side. Let me make sure I didn't miss any steps. H naught to the 1/2 and you square it. Perfect, okay? So this is now H as a function of the time with your initial conditions, okay? So that is how you solve it. Now let me show you my MATLAB script, which is right here. Bring this down for you so you can see it. Okay, so I have my header up here, my main code, so clear, CLC, close all. Here's my givens: diameter of the jet, the tank, acceleration due to gravity. I find my areas. I initialize my numerical method, so delta T is 0.1. I'm going to run this to 60,000 seconds. My initial H is 3 meters. My initial time is 0. Down here is a for loop to solve for the height. So this right here, this is the numerical method, okay, where you have your differential equation and you're marching ahead in time. Make sure you watch the video on how to do the numerical method. That's how to create and explain how we get this. And then again, we find time by just adding our delta t to our last time, okay? The numerical method, again, watch the video that I describe how to do this, and then I plot it, okay? Now, why am I showing this? Because down here, this, or really line 53, is that equation that I just solved, right? It is the theoretical method after solving that differential equation, okay? And so I basically take that equation and I plot on top of my numerical method to make sure that they match, okay? And let me show you the graph. So once you plot it, they line right up with each other, okay? So I know that my theoretical and my numerical method, if they're both getting the same answers, then I'm probably pretty accurate in my solution. Okay, thank you. I hope this helps, and if you have questions, let me know. Bye now.